Hello everyone, welcome to David Griffiths Electrodynamics. This is going to be problem 4.27 from the book. So, in this problem, we're asked to calculate the work using two different equations, 4.55 and 4.58, for a sphere of radius r that has a uniform frozen in polarization P. So it's not necessarily a linear dielectric in this case, it's just a dielectric with some polarization P in it. Comment on the discrepancy. So it's saying that we're going to have some kind of discrepancy between the values for the work done using both of these equations, and then which is true if either. What is the true energy of the system if either of them? So let's just kind of look at this problem. And this setup of the problem is exactly the same as example 4.2. It tells you that in the problem. So we're going to use those results from problem 4.2 rather than having to solve that again for this. So we have this sphere of radius r with some polarization P due to some external field that we're not really interested in. Or actually, it's a frozen in polarization, so it's some material that got polarized and then the electric field was turned off, and now it's just polarized. So there's no external field going on. It's just now there's this polarized material and it's sort of frozen in there. So it stays there even if the electric field that caused the polarization is turned off. And I split this into two regions, so 1 and 2. 1, of course, is inside of the sphere. Region 2 is outside of the sphere. And then equation 4.55 is the work done by the electrostatic force. So this is essentially the work stored in the field versus the other equation, 4.58, is the one we used on the previous problem, where it's the work done to assemble free charge due to a dielectric material, which in this case, there is no free charge in this problem, so we'll see an interesting answer to that. But let's start using this equation. So let's calculate the work done of this configuration using this equation. So what we're going to need then is the electric field for both regions due to this setup, which is derived in problem or example 4.2 in the book. So the potential in both regions is, so inside the sphere, it's P over 3 epsilon naught r cosine theta, and then outside the sphere, it's P over 3 epsilon naught capital R squared, or capital R cubed over little r squared. So we have the potential, and then we can use the fact that the electric field, of course, is the negative gradient of the potential to derive the fields. So we just have to take the derivatives of these, we have to take the gradients of these and apply a minus sign. So I'm not going to do that. It's a fairly simple relation. Just look up the gradient in the front cover of the book and then do those derivatives, and you'll get this for the electric field. So inside the sphere, the electric field is a uniform field that is minus P over 3 epsilon naught in the z direction, where z is just whatever axis you decide to choose, really. And then the electric field outside the sphere is P over r cubed, capital R cubed over 3 epsilon naught r cubed times 2 cosine theta plus sine of theta. So there's both an r and theta dependence on the field outside of the sphere. It's not a uniform field outside. So we have the electric fields. Then what we need to do is integrate over all of space, and we need to integrate not the fields but the squared magnitude of the fields. So we have to calculate those. So the squared magnitude of the field in region 1 is just going to be P squared over 9 epsilon naught squared, and then the squared magnitude in region 2 is going to be, we just take this relation here and calculate the dot product, and we just calculate the squared magnitude of those. So we just take the magnitudes of the fields and multiply them together. So what we get is P squared capital R to the 6th over 9 epsilon naught squared little r to the 6th. Then in parentheses we have 4 cosine squared of theta plus sine squared of theta. All right, so we're going to take these two expressions for the fields and plug those into our work integral. So using equation 4.55, we have epsilon naught over 2 times, and then the first integral is going to be in the region 1. So if R is going to go from 0 to capital R out to the surface of the sphere. And so we have to integrate field 1, which is p squared over 9 epsilon naught squared. And we're integrating with, over the volume of that sphere. So we have to use d tau in spherical coordinates, which is r squared sine of theta, dr d theta d phi. Where for both of these integrals, I'm, well, at least for this integral here, I'm not writing down the theta or phi integral. I'm just sort of going to evaluate it because I know it's going to be 4 pi because there's no theta or phi dependence, and I know that the integral of sine of theta d theta from 0 to pi is 2, and the integral of d phi from 0 to 2 pi is 2 pi, so we get 4 pi. But for the second integral for over region 2, where it's going to go from capital R to infinity, we're going to be, I pull out all the constants, but we end up having a 1 over r to the 6th from here. And then, of course, we have the r squared from the volume element. So that's going to make that a 1 over r to the 4th. And then, but we do have a theta integral here, or theta dependence here. So we do have to do a real theta integral. So this is going to be sine of theta times 4 cosine squared of theta plus sine squared of theta d theta. And of course, theta ranges from 0 to pi. And then, of course, we just have the phi integral, which is just d phi from 0 to 2 pi. That's going to be just 2 pi, of course. Now, this integral, I believe you can solve this maybe with u substitution, but I just plugged it into an integral calculator because I just wanted to, it wasn't the purpose of the problem. But I imagine you can either solve this with u substitution or some kind of trig identity to get it into, use some trig identities to get it into a nice form, and use some relations that way to solve this integral. But the integral itself turns out to just be 4. So I just used that result in this problem. And so what we get then for the work here is we still have our epsilon naught over 2. We have our p squared over 9 epsilon naught squared. We have our 4 pi from the first integral, from the phi and theta integral. And then from the r integral, we get the capital R cubed over 3 from here. Then the second integral, of course, we have all these constants, p squared r to the 6th over 9 epsilon naught squared. This r integral gives us a positive 1 over 3 capital R to the cubed. And then, of course, we have a 2 pi from the phi integral, and then we have a 4 from the theta integral, so this gives us an 8 pi here. So then this is really just a matter of doing some algebra and trying to just simplify this down into as compact form as possible. Of course, this is correct. You could leave it like this, but it's just nice to try to compact it all as nicely as we can. So of course, this is just a matter of just doing some algebra. So my initial step was just to multiply the epsilon naught and the 2 through, and multiply some constants. So we end up having a 2 pi over 27 because the 2 and the 4 pi cancel, and then we multiply the 9 by the 3. And we get 2 pi over 27 times p squared capital R cubed over epsilon naught. And then the second term, I end up having a 4 pi over 27. That way we get the same denominator, and we get p squared over capital R cubed over epsilon naught. And then adding those 2 pi over 27ths plus 4 pi over 27ths, that gives us a 6 pi over 27ths, which is just a 2 ninths. So our final term is just 2 pi over 9 p squared capital R cubed over epsilon naught. And this is going to be the total work done. This is the total work, or sorry, the total energy or work to, that's stored in the electromagnetic or in the electrostatic field for this configuration. All right, so that was a lot of integrals and algebra there, but we're halfway done now. So, like I said, this is the correct electrostatic energy to configure the system, but it doesn't calculate the work that's done to polarize the molecules and such. So there was work already done, right, by some external field that polarized the sphere, and so the molecules had to then stretch and pull apart, and there was work done to do that. But this this expression doesn't take into account that work. So this is only the work done. This is only the work to sort of assemble the system, but not the work that's done to polarize the molecules, if that makes any sense. So let me go back up. So yeah, so we're here. Okay. Now let's look at equation 4.58. So 4.58 tells us this. However, what we know is that this work is not the work done to assemble the system per se, but it's the work done to assemble any free charge into the system that has a dielectric, of course, and when there is no dielectric, this just reduces to the other equation, but we have no free charge in the system. So I'm expecting this work integral to be 0, but let's see. So what we're going to need then is, of course, we're going to need the displacement field inside the sphere and outside the sphere. We already have the electric field, but we need a displacement field. So for r greater than r, we know that there's no dielectric out there, so D is just epsilon naught E. There's usually a plus P here, but there's no polarization out there, so it's just epsilon naught E. So the contribution then outside the sphere is just the same. It just turns into the E squared equation. If you plug in this into here, you just get epsilon naught over 2 E squared. So outside of the sphere, for using this equation, it just reduces to the previous equation, which is what we expect. There's no dielectric material out there. So the contribution to the work is going to be exactly the same. So that contribution was region 2's contribution. So it's the answer to this integral here, essentially, the second integral. So it's going to be this term here, which I don't have, so it's actually going to be this one right here. So this is the work done, this is the work done from the electric field in region 2. So this contribution is going to be exactly the same in this case because there is no polarization outside. So we can basically just use that answer, and all we need to do is evaluate the work done inside the sphere and then add those two together. So for inside the sphere, we know that the displacement field is going to be epsilon naught E plus P. And we know that the electric field inside the sphere can be written as minus P over 3 epsilon naught. And then if we plug that in, we just get a minus P over 3 here because the epsilon naughts cancel. So we get minus P over 3 plus P, which is just a 2/3 P. And then we can rewrite this in terms of E by the fact that we know E is minus P over 3 epsilon naught. So P is equal to minus 3 epsilon naught E. So then D, if you plug in this expression for P into here, then D is equal to minus 2 epsilon naught E. So then we can use this for D in this equation here. So 1/2 D dot E is the same as 1/2 times minus 2 epsilon E dot E, which is the same as minus epsilon naught E squared, which then we know the field inside is, of course, P over 3 epsilon naught. So we get a minus epsilon naught P squared over 9 epsilon naught squared, which is minus P squared over 9 epsilon naught. So this is 1/2 D dot E inside of the sphere, region 1. So then we just need to integrate this to, that to get the work contribution. So if we integrate that, we end up getting, a minus sign, and then we're integrating for region 1. We already know the work done due to region 2. It's the same as the previous part. So this goes from R equals 0 to capital R, and there's no theta or phi dependence, so we know that's going to be 4 pi for those two integrals. So there's the 4 pi from there. And this integral we're doing is just r squared dr, which just becomes capital R cubed over 3. And then multiply these together, you get a minus 4 pi over 27 times p squared r cubed over epsilon naught. Which, if you look at this is exactly opposite to the work done outside of the sphere. So when you add up the two contributions, the two integrals, you get 0. So this contribution will completely cancel the contribution outside the sphere. So the total work done is 0, which is kind of what we would expect, because this equation for the work only is the work done to put any free charges onto some dielectric material. But in this case, we have no free charges, so the work done should be 0. We do no work to put any free charges. There was work done to polarize the sphere, but this equation isn't calculating the work done to polarize the sphere. This is the work done to put free charges onto a dielectric material that's already polarized. All right, so I hope that makes sense. If you guys have any questions, comments, or concerns, feel free to let me know in the comments below. Leave a like, subscribe, and check out my membership options to my channel. Otherwise, like always, I will see you guys on the next video.